Does anyone have any pending spectrogram questions? The sun keeps coming out and going back, so I'm going to be getting bright and then dark all lecture. That's okay. Anyone have any pending spectrogram questions? Seems like things are going generally okay. Most folks hit the week 1 checkout without much issue, and then the observation has mostly been that unintentionally, it seems like the week 2 checkout, once you hit that week 1 checkout, is not too much trouble. So we've had a lot of people hit the first checkout and then a half hour later be done with the lab. So, which is not to say necessarily that's going to be the case for everyone, but it just seems to be an observation. If there are no questions or bugs with spectrogram, I'm going to start talking about Lab 4 a little bit. I think we'll introduce Lab 4 today and see how far we get, and probably conclude introducing it on Monday. And then, like I said last time, I think next week, maybe Wednesday, we'll do another final project discussion, maybe a little bit more specific than last time. If folks are having some specific ideas about what they'd like to do, we can talk through that stuff and just some of the logistics of it. And then, yeah, sometime maybe end-ish of next week, we will transition to from lecture to additional lab time. And we'll have a conversation about when to place that additional lab time. Clearly, this time is free for everyone. So perhaps it makes sense just to substitute lab time in for this lecture time, perhaps adding a little bit to the end of it. In any case, anything from anyone before I get started? Okay, so I'm going to share my screen. What I try to do with these labs is they're all a bit different, as folks have observed, and the hope is to provide people with various interests a lab that suits whatever your specific interests may be. So this final lab is the best I could come up with for a remote learning robotics lab. So for the roboticsy people in the class, this is the best version of a robotics lab I could come up with in the circumstances. And the idea, as you may remember from the very beginning of this class, and as I'll demo again today, is to control a pan and tilt robot. A little two servo motors, one in a pan configuration, the other in a tilt configuration. And the idea will be to give it a little personality and make it somewhat interactive. Before I get into the details of the lab itself, I want to talk through, we've been the past few lectures, we've been stepping through a few different sorts of motors. The motor of relevance for Lab 4 is going to be servos, so I thought I would take just a few minutes to talk through servo motors and at a high level, sort of how they work and how we interact with them, and then I'll show you specifically how we'll be interacting with them for Lab 4. So let me get started with doing that. Servo motors are usually servo motors are used for position control. So this is different than something like a DC motor, which we talked about the previous couple lectures, which are more generally used for, without feedback that is, they're more generally used for just getting something to spin at some rate. Servo motors usually are used for controlling something to a particular rotational position. Much like a stepper motor, except that the means by which they achieve a desired position is different from the stepper motor. In the stepper motor, that position is achieved largely as a consequence of the internal mechanism of the motor. So I'll just remind you, but you'll require that the internal mechanism of a stepper motor involves a series of these metal cores. There's only 2 shown in this picture. In an actual stepper motor, there are many, many more. The notion being that we can use coils of wire to magnetize these cores in order to set up a stable configuration for a rotating central permanent magnet. And depending which of these cores we magnetize, the stable configuration for that central magnet is different. So it'll pop from this orientation to a horizontal orientation in this picture when we demagnetize this core and magnetize this core. So position knowledge is really a consequence of the construction of the motor in this case. The servo motor is a little bit different. The way that a particular desired position is achieved in a servo motor is by means of feedback. So in a servo motor, you specify some desired position for the motor. As we'll see, you actually you encode the desired position as the width of a pulse. The control input to a servo motor is a pulse train. We'll talk more about this, but you communicate the motor to the desired position by means of a pulse train, where the widths of those pulses are, each width corresponds to some desired position, so you tell it the position that you'd like. It uses some sort of sensor to measure the current position of the motor. In a high-end servo, this may be some quite sophisticated encoder. In the sorts of servo motors that you are likely familiar with interacting with, the sort that you would buy from like SparkFun, this is generally just a potentiometer. So the idea is that the motor output shaft is connected to a potentiometer, and as the motor turns, it's turning the potentiometer, so that each different position of the motor corresponds to a different measured voltage across that potentiometer. So it's a means of measuring the position of the motor. So the desired position is compared to the measured position. That position error is sent into a controller, which is generally built into a little PCB that's built into the servo motor that has some control mechanisms in it. That controller converts the position error to a voltage commanded to an H-bridge circuit that drives a DC motor, which causes the DC motor to turn in a direction that reduces this position error until the position error is 0, at which point it stops rotating and will sit mostly still. Servo motors, they may quiver a little bit, but mostly they sit still. So the idea is you send a desired position, it compares the desired position to the measured position, measured by means of a potentiometer in the servos that we use, and moves a DC motor until the measured and desired position are the same. As close to the same as is possible with the sensors that we're using for feedback. Many of you may, in your previous classes, I think in 3400 you use modified continuous rotation servos. The same is true in the MAE mechatronics course. Is it clear based on this picture the modifications that you would have to make to a servo to make it continuous rotation? So if you bought a servo from SparkFun and you wanted to convert it from a position control device to a continuous rotation device, the thing you mess with, so you take this thing apart, and the part of this that you mess with is this feedback part. So there are a few different strategies for doing this. A common one for converting a servo motor to continuous rotation is you open the device up, you turn the potentiometer in there to about its center position, so that the feedback here is always there. The motor is always being measured to be at its central location, and then you cut the feedback line between the motor and the potentiometer, so that regardless of motor position, you're always measuring the potentiometer to be at its central location. And then the notion is that if you send in a pulse train that commands the motor to its center position, well then it will measure. It's not really measuring anymore because we've cut the feedback, but it will measure the same, the desired and the measured position of the motor will be the same, and it will sit still. If there's any difference, then the motor will start to rotate, but because you've cut this feedback line, it will keep chasing that position forever, which means it's set up in a continuous rotation configuration. And the bigger the difference between the commanded and measured positions, the faster it rotates, and it will rotate in either direction. Okay, so you've probably used those in some of your classes, and that's how you do that. So this is the schematic version of what's going on in a servo. This is sort of an exploded view of a servo motor that shows the components in this schematic sort of more mechanically, visually. So the notion is there's some DC motor in the servo that is high speed, low torque. This DC motor goes through a gear train that reduces the speed and increases the torque of the output. The end of this gear train, the actual output shaft of the motor, is connected to a potentiometer that rotates with the output of the motor, so that the position of the motor can be measured. That measured position is fed back to a control circuit, which sends, which converts the difference in desired and measured positions to a voltage to an H-bridge and commands this DC motor to turn. In a high-end servo, this gear train may be some sort of a metal. In most of the servos that you use, this is a plastic gear train here. The other modification that's often required in order to make a servo continuous rotation is it is often the case that this final gear has some sort of a stop on it to prevent it from rotating beyond some threshold. So often you have to take apart this gear train and cut whatever mechanical stop there is on this last element of the gear train. By the way, it's pretty common in a lot of these classes for when you give a student a servo for them to grab the end of it, go and twist it back and forth. Not exactly sure why. It is kind of tempting for some reason. That can destroy the motor. It's because of this whole gear train here, and you are putting a lot of stress onto the servo. So if you buy a servo, avoid the temptation to back and forth with it, because you will, in all likelihood, destroy it. An unusually common failure mode for these servos in those classes is twisting them back and forth. Any questions about this? Folks have worked, I imagine that almost everyone in this class has worked with servos before, but perhaps you haven't looked at the guts of it. So these are the guts of it. As I mentioned, we control the input to these servos by means of a pulse train. So the command input to a servo motor is a sequence of square wave pulses, and the period of the whole pulse train is 50 hertz, which is actually quite slow in comparison to other things that we've been experimenting with. So a 50 hertz pulse train, and the position is commanded by changing the width of this pulse. So if the width of this pulse is 1 millisecond, plus or minus some amount, this often takes some experimentation, but about 1 millisecond generally corresponds to a leftward position of the motor. 1.5 milliseconds points the motor in its center orientation, and 2 milliseconds points it right. I'm going to show you a demo of this in just a moment, but we change the commanded position of the motor by changing the width of this pulse. The period of the whole pulse train stays the same, so it stays a 50 hertz pulse train, but by modifying the width of that pulse, the duty cycle of the pulse, we change the commanded position of the motor. Okay. So as usual, I want to look at some code to show how we do this on the PIC32 specifically. Before I do this, let me talk a little bit about Lab 4, just kind of introduce and motivate it. Any questions so far? Has anyone had any other failure modes of servos? They're notoriously a bit finicky. Not uncommon for them to fail. Which means, by the way, well, I guess we'll get into this as we talk about the Lab 4, but we are opening ourselves up for a lot of potential issues in Lab 4 because we have things moving. So if things get a little wonky in Lab 4, just be patient.
I've seen one other failure mode fairly commonly, and that is to say, people think it's the servo is a DC motor, and they change the polarity to make it go in the other direction, and smoke comes out.
So let me sort of introduce the philosophy of Lab 4, because Lab 4, I mentioned this in, I think, lecture 1 or 2 of this class, but Lab 4 is a little bit different in flavor than the other labs. In Labs 1, 2, and 3, the objective has been to create some tool through which you can either, what am I trying to say? You create a tool of one flavor or another. In Lab 1, we sort of created a sandbox for understanding bird songs. So the idea is that it's a tool for composing bird songs. In Lab 2, we created a sandbox for understanding flocking. In Lab 3, we created a tool for doing spectrograms. Lab 4 is a little bit different in that the objective here is really to create something that makes you smile, is the goal. You're trying to create something that when you play with it, it is endearing, which is an unusual and sort of can be a remarkably difficult objective, actually. Create something that makes you smile is kind of a hard engineering objective, but we have a few suggested strategies for doing that. The idea will be, we're going to have two, well, let me show you, let's see, let me show you a demo. So what I have set up on my bench, you may remember this from a while ago, is a little robot here on a pan tilt servo assembly. As I've mentioned previously, the rangefinder here is non-functional. It's just because it kind of looks like eyeballs, and you'll have some sort of an eyeball-looking thing on your robot. And the notion is that we can, by means of the Python interface, change the direction that this little guy is looking. So we can pan around, and we can tilt up and down, and we can make him look directly at the camera. And by the way, let me just show you. What I have scoped here on the picoscope right now are the two control inputs to the two servo motors. So one of these is the pan motor, the other is the tilt motor. I don't remember which is which, but we can find out. So let's see, pan. So blue is pan and red is tilt. And this is showing you the pulse train that is being sent to the motor. So that you can see that this is a 50 hertz pulse train, and as we change the position, where's my camera? As we change the position of these motors, the width of these pulses changes. Okay, so at one extreme, it is all the way right. At the other extreme, it's all the way left. And somewhere in the middle, it's somewhere in the middle. And the same is true for both these things. And the notion for Lab 4 will be, you will create an interface that allows for you to program a particular position, a return position of the robot. And then once that position is programmed, you can deselect, and the robot will look around. And then when you speak to it, I don't have it hooked up with my voice right now, so I'll just use this return to position button. But the notion is that when you speak to it above a certain volume threshold, you yell at it, so to speak, it will return to its position and look back at you. This is sort of the minimum required behavior for Lab 4. And the hope is that folks will figure out other ways to imbue this little robot with other sorts of personalities. So maybe it doesn't always look back at you in the same way. As set up right now, when it looks back, it sort of snaps back as quickly as it can manage. A different personality might be sort of communicated if it were to turn back slowly and look at you. And if it were to oscillate between looking back quickly and looking back slowly, that might give it a certain different kind of personality. If instead of looking up and around, it did something else, that might give it a certain kind of personality. So the hope is that this is sort of fun and open-ended, and the challenge is how much personality can you give this little robot that is so constrained. You know, all it can do is pan and tilt, and the only means by which you can interact with it is a Python control interface and your voice. So what can you make it do? That's the question. Any questions about the objective of the lab? You will generate these pulse trains using a hardware peripheral called the output compare module, which we'll spend some time discussing. The output compare module provides you a means of creating essentially a pulse width modulation pulse train for which you can dynamically change the duty cycle of that PWM signal, which is exactly what we want for controlling a servo motor. But we'll take a look at that in a moment. The other thing I'll just point out about the lab write-up itself, and this is an observation that some of you have made, is the lab reports from lab 1 to 2 to 3 to 4 get a little bit sparser. The idea being you're getting more comfortable with this platform, so you are getting more comfortable with going to the documentation to figure some things out on your own. So it's a little bit less explicit with precisely how to do things. And of course, if there's problems with this, we can absolutely cover stuff in lecture. But the idea is that we're stepping back a little bit as we move towards final projects, where we sort of step back totally. Okay, any questions? Okay, so the next thing I'll talk about then is using the output compare module on the PIC32 to actually generate these pulse trains. And I will start by just looking at the hardware reference manual chapter associated with the output compare module. In comparison to some of the other hardware peripheral systems that we've been using, this one's quite simple, actually. Way less configurations than something like the analog to digital converter. You'll also need the analog to digital converter, incidentally, in this lab, because you are tasked with making the robot do something when you speak to it. So the analog to digital converter is going to be used to be sampling the audio input to the PIC32, as it is in Lab 3. So the ADC configurations for Lab 4 and Lab 3 will be identical. They're just going to be used differently. In any case, we can look at the output compare module. And so this is the block diagram of this system. What the output compare module does is it allows for you to set the values of 2 compare registers and to specify a timer. And all the output compare module does is compare the current value of the timer to the value in those registers and take some action when there's a match. And the action we will configure this such that every time it sees a match between the timer value and one of the compare registers, it will toggle its output. So you will configure one of these compare registers to be 0, so that whenever it sees a 0 in the timer value, which is to say the timer has overflowed, then it will toggle. And you'll set the other compare register to whatever it needs to be to achieve the duty cycle that you require for the servo motors. So you configure this thing. When the timer starts, it starts counting up, and when the output compare module sees the same value between the timer and the second compare register, it will toggle low. And then when the timer overflows, it toggles high again, and then it'll toggle low again. We'll look at a timing diagram of this in a moment. But it should be clear then that the period of that pulse train is then controlled by the overflow value of the timer. And the duty cycle is controlled by the value of that compare register. See this in a moment, okay? So you can open this in a number of different modes, and we'll talk through a few of them, but I want to spend time discussing specifically the mode that's going to be relevant to us, which is PWM mode for the output compare module with default pin disabled. So this is just showing you the other configurations for the output compare module. Turn it on or off. Stop in idle mode. You can configure it to 32-bit compare mode, which, depending how you set things up for Lab 4, you may want to do. The period that is required here, or the frequency that's required, which is 50 hertz, is that period is too long to use a 16-bit timer with a prescaler of 1. So you have a few options here. One of your options is to chain two 16-bit timers into a single 32-bit timer so that with a prescaler of 1, you can count up high enough to achieve the period that's required to control the servo motor. That's one option. Another option is to change the prescaler value of the timer so that it doesn't increment every CPU cycle, but perhaps every 4 or 8 or 16 CPU cycles, so that you can get the length of time for your period that's required for controlling the servo motor. So you have a few options here, but this 32-bit compare mode may be of relevance depending how you set things up. It allows for you to point the output compare module to a particular timer, timer 2 or timer 3. You can chain timer 2 and timer 3, each of which are 16-bit timers, to a single 32-bit timer. If you do that, you point it to timer 2, and it will see the changed timer 2 and timer 3. In any case, let's take a look at this timing diagram. This is showing you the timing diagram for a bunch of modes that are not of relevance to us for this lab. So if we scroll down to PWM mode, down, down, down. Let us see. No. PWM mode, here we go. Okay. Is this what I want? I believe so. Yeah, this is what I want. So what we see here, this is the output pin of the output compare module, which, by the way, is mapped with peripheral pin select. So you need to map the output compare signal to a particular I/O port using peripheral pin select in a very similar way that we mapped the SPI signals for communicating with the DAC. You'll need to map the output compare module to the I/O ports that are connected to the servo motors. So this is the output pin, and what you can see is that it is toggling. It's going high and then low with some period. And what it is doing is comparing the value of timer 2 in this case to two compare registers. And it is toggling, in this case, it is toggling when it sees a match between timer 2 and this first compare register, which is configured to 0. Am I reading this properly? Maybe this one's easier to look at. Yeah, it's comparing the value of the timer to the value in these two compare registers. And when there is a match between the timer and either of these compare registers, it toggles the output. So one of these compare registers will be set to 0 so that it's toggled when the timer overflows, and the other compare register will be set to whatever it needs to be in order to achieve the duty cycle that's required to steer the servo. Which is what is supposed to be represented here. I'm having trouble reading this timing diagram because it's not clear to me where they're specifying the value in these control registers, but in any case, that is what's going on. So that's all that's happening. We can look at some PLIB code to take a look at how you actually configure this thing. Questions about this, though? Is this relatively clear? Okay, so let's look at some code in that case. So, let me see here. Yeah, let's look at some code. I'm going to stop sharing my screen just a moment just to make sure the code that I have up is not all the code that you need for Lab 3. Okay, it's not. So, share my screen again. Okay. So this is the code that we're looking at right now is the code that you would use to set up two output compare modules to control two different servo motors. And like I mentioned, there are a few different strategies by which you can achieve the required period for that pulse train. One is to change the prescaler value to something other than 1 so that you count more slowly. The other is to chain a couple of timers. In what we're looking at right now, we're chaining timers 2 and 3 in order to build a timer that can count for long enough in order for us to achieve the desired period of our pulse train. So what you can see is we are opening timer 2, 3, which means we're opening timers 2 and 3 in a chained configuration. And then we're doing a bunch of stuff here that should at this point look familiar with just one sort of unusual detail. We turn timer 2 on. Now that timers 2 and 3 are chained, we can do configurations for timer 2, and it's really talking about the chained timer 2 and 3. So we turn timer 2 on. We set its source to internal, its timing source to the internal clock. Set the prescaler to 1. Importantly, we turn it on in 32-bit mode because we've opened this in a chained configuration. So now, instead of a single 16-bit timer, we have a chained 32-bit timer. And as usual, we set the overflow value of this timer, which is set to 800,000 cycles, which is more cycles than you could fit in a 16-bit timer. But 800,000 cycles, if you divide 40 megahertz, so 40 million by 800,000, you end up with 50 hertz. So this is generating a timer that will overflow at 50 hertz, which is what we want. We configure the interrupt for this timer as usual, except that instead of timer 2, which is what you've generally been working with, it's timer 2, 3 now, and clear the interrupt flag. In that interrupt in this lab, we will be doing things like changing the duty cycle of this pulse train to move the servo to a new location, and doing analog reads of what the user is saying into the microphone. We then open the output compare module, turn it on. We point this output compare module, output compare module 3. We point it to timer, we open it in 32-bit mode. We point it to timer 2. We disable the PWM fault pin. We don't need it for this lab. We set these final two parameters here are setting the values of those two compare registers. The first compare register is set to 0, and the second compare register is also set to 0. It doesn't really matter what you set this to when you configure it because you're going to be changing it in your program. Or at least it doesn't necessarily matter. Depending how you set things up, maybe this matters, but because as I have this configured, I am changing the period of that sine wave, of that pulse train in an interrupt service routine. This will be changed as soon as the threads start to run and the interrupt service routine starts to run. And then, importantly, we use peripheral pin select to map the output compare 3 signal to pin RPA3, which is one of the pins to which the servo is connected. So let's just look at the peripheral pin select page quickly. Let's just look at this. So if we go to the I/O page, you will remember from many lectures ago we were talking about I/O ports. If we look for the output compare signal names on this diagram, we're not going to find them, and that's because output compare is mapped by peripheral pin select. So instead, we need to go down to the PPS output table. And what we will see is, for, let's take as an example, output compare 3, we can see all of the I/O ports to which we can map the output compare 3 signal. So we could use peripheral pin select to map to any of these that we would like. you are mapping to the one to which it's a little bit backwards here because the servo is already hooked up. So I'm telling you the servo is hooked up to RPA3. So that means you know which of these mappings you have to do, right? This is not really a degree of freedom for you in the way that it would ordinarily be. But in any case, this is where that mapping takes place. And then we're also using output compare 4 to control the other servo. And you can see the library of I/O ports to which we could map output compare 4. Okay. So we map the output compare 3 signal to RPA3. Remember that this is just specifying the group number, right? The group number, group here, 1, 2, 3, or 4. That's all that's specifying. And we do the same for output compare 4. Turn it on, 32-bit mode, point it to timer 2, turn off the PWM fault pin. First compare register is 0. Second compare register doesn't matter because we're going to be changing it as soon as we hit the interrupt service routine. So that is just initialized also to 0. Map that using peripheral pin select. And then the whole thing starts. And in that interrupt service routine that's tied to this timer, which will be triggered every time a period of that pulse train is finished, we will reconfigure the duty cycle of these two output compare modules if necessary, depending on the user input. And we will sample the analog pin to see if the user has spoken to the robot and take action if necessary. Questions?
Will the interrupt given by the chain timer 2 and 3 will be triggered by only the timer 3 because we are just clearing the third timer's interrupt flag?
So I'm not sure I understand the question. Are you asking which interrupt flag gets associated with the chained timer?
Yeah, exactly.
It will be, let me just double check here. I'm going to stop sharing quickly so I can scroll up. I believe it's timer 2. Pretty sure it's timer 2.
There's a complicated set of rules for which flag gets set where, and you just have to read the timer hardware manual to get the rules right. There's no substitute for that.
Yeah, and I lied. In this case, it's timer 3. But you will have to read. You'll have to read the manuals here for this one. Okay. Lab 4 questions. Any Lab 4 questions? Not at this point. Okay. How about Lab 3 questions? How about final project questions? What do people think? We got through this a little. I'm doing this because I'm kind of killing time. We got through that content faster than I imagined, so we have about 10 minutes to spare. So we can kick around some project ideas.
When is the project proposal due?
So I'm going to have the project proposal due on the same day as the Lab 3 report. So that is going to be for the Monday people. That will be a week from Monday. Okay.
Yeah, so what I found interesting looking on different ways to use Ethernet on the PIC. I'm still thinking about that. Mm-hmm. I looked at Alex Whiteway's paper that you had on the course website, and it looked like he had designed, among other things, an Ethernet board that I guess works fairly well with the PIC. I don't know. I'm looking at the paper again to see exactly how much testing he did of that specific board, but do you suggest trying that board or just picking out any promising looking SPI Ethernet board. Because the impression I got from that paper is Ethernet is something that it's most useful to have a coprocessor for, so then you can have the proper driver for the actual port as well.
I seem to remember that Alex Whiteway's project used a fairly simple Mac Fizz level chip, right? So it handled the extremely high speed stuff, but none of the TCP/IP protocol. Am I remembering that right?
Yeah, I think that was the impression I got. So because it's a teaching board, so then you could just explore getting data to the physical board fast enough to implement UDP or TCP over IP.
Right. Yeah. Do you remember what year that was?
That was May 2015. Or Alex got his MEng in May 2015, so I assume is that year.
Oh, that was actually an MEng project. Or was it
Yeah.
an MEng project?
Yeah, it was his MEng project.
Okay. Let me just take a quick look here if I can find that. 2015.
And then apparently Microchip does provide some kind of TCP/IP stack, but the impression I got was that it wasn't trivial to get the code up and running on our PICs. He did have to go through some debugging and some process. It wasn't just drag and drop onto the board.
That's for sure. And part of that is that much of the high-level protocol stuff for the PIC32 is now written in another library called Harmony, which in my impression is more like Discord, but I can't make head nor tail out of Harmony. But that may be because I was looking at too early a version of it. I can't just put my hand on Alex Whiteway's stuff right at the moment. So
we can maybe talk about that in lab.
Yeah, let's talk about it in lab.
Yeah.
I would say if you're going to write it yourself, you probably don't want to write TCP/IP. You probably want to use UDP. It's my impression that most of their Ethernet stuff also runs on the 700 series or the 500 series rather than the 200 series of PIC32s. They have a lot more memory. Let's talk about it in lab.
What are other folks sort of zeroing in on? Or are folks still kind of, if you're still not sure at all, that's okay. Is anyone else sort of zeroing in on an idea since the last time we spoke about this stuff?
I'm sort of trying to implement the Dino game, but it's pretty unoptimized to be honest. So I'm looking towards using DMA to display to the PIC to the TFT, but it's still under process. I still can't figure out how to use DMA.
DMA to the TFT display. Yeah. As I think was mentioned in an email exchange, that has been done in the past. A couple of students have figured that out. I'm not sure how they did it. And so we can be helpful to the extent that as you figure this out, if you come across something and say, is this what this means? We can maybe say, yeah or no, that is or isn't what that means. But that is going to require a lot of low-level digging, which is good, but just so that you're aware. And the other thing to mention with regard to that stuff is you can get a low fidelity video game running without doing, like, the DMA to the TFT is not a critical aspect of getting a game like that running, right? It's a nice aspect, but you can get a version of that game running without doing DMA to the TFT. So I would, to the extent that's possible, do the two in parallel. Build a low fidelity game using low fidelity graphics that just gets the mechanics figured out of jumping and ducking and doing the stuff that happens in the Dino game. And then, if possible, use DMA to the TFT to perhaps improve playability or improve graphics or whatever it may be.
Another possibility is to, instead of using the TFT, is to use an old style NTSC television, analog television, of which we have a few in the lab. The nice thing about NTSC televisions is that the DMA interface to the television is completely worked out. And you can drive full, the overhead for running the television is about 2% of the CPU. So you can make a bigger display with probably about the same resolution or a little higher resolution, but probably 4 levels of grayscale only, no color. That's the trade-off, but it is fast.
Sure, maybe I can take a look at it.
One group of lunatics one year got VGA running, full color VGA running as a final project. That is documented.
Is that the group which implemented breakout on the VGA
Yeah.
display?
Yeah.
I looked at the project and it was precise down to nanosecond scale, right?
Oh yeah. It was hurtful.
It was amazing. Like I read the documentation and I wanted to implement something like that. So I was looking at it last night.
So we've about a minute remaining. Is there anything that folks would like to revisit? So we've covered a lot of topics in this class. Is there anything, you don't have to answer this now, you can also send me an email or you can put it in that Google form that's on the Canvas homepage. But if there's anything that you would like to go back to and just talk in more depth or talk again about, let me know. We do that a few times in 5760 for some of the trickier topics, and very happy to do that. So if people want to revisit direct digital synthesis, if you want to talk a little bit more about fixed point, if you want to talk in more depth or again about any of the communication protocols we've discussed, just let me know. And we can revisit some of those things as you head towards final projects. Okay. All right. I'm going to have office hours today from 12 to 2. So if anybody would like to come hang out, I will be there.